Electrolytes are all ionic compounds that are water soluble. Ionic means metal to nonmetal, positive to negative. Consider charges when you crisscross. Those are ionic compounds. The 7 strong acids. Shall we list them? Let's do that right now. HCl, hydrochloric, is a strong acid, will 100% dissociate. HBr, hydrobromic. HI, hydroiodic, all binary strong acids. Chloric acid, HClO3, and perchloric acid, HClO4. Notice the polyatomic chlorate, 8 turned to ic, so we get chloric. Here's the polyatomic called perchlorate, so the acid turns to ic and you get perchloric acid. Hydro root word ic for binary, and then the last name here comes from the polyatomic ion. Hydrochloric, hydrobromic, hydroiodic, chloric, and perchloric. We also have nitric, coming from the polyatomic nitrate, and 1 polyprotic acid, sulfuric. Sulfuric is known as battery acid. It is indeed strong. There are 7, and that's it, only 7 strong acids. And friends, if you memorize those 7 strong, or have them handy to write down, you now memorize that all of the others, anything else starting with H, is considered weak. Strong versus weak. An acid is either strong, only these 7, or it is weak. Weak acids only partially dissociate. And for instance, this is showing acetic acid. This is commonly called vinegar. Acetic acid is not one of the 7 strong, so it sets up an equilibrium. I prefer showing an equilibrium that illustrates that it's favoring the molecular side, hardly dissociating at all. The process of an equilibrium makes more sense to me than this double arrow that they have in our text. That process of breaking apart is called dissociation, to separate or to fall apart. Literally, what we're going to show in dissociation equations is taking each of those ions and writing them in terms of showing their charge. Sodium sulfide, when I say the name of this compound, sodium sulfide, lets me know what ions to break it apart into. Sodium sulfide is written based on charge, +1 and a -2, so we crisscrossed and found that formula, Na2S. When it dissociates, it separates into the ions, and ions carry charges, and it's those charges that are lighting up that bulb. I need to show the charges on the dissociated form, letting you know that it's an electrolyte, indeed a charged ion. 2 sodium ions are released, and 1 sulfide ion are released. The dissociation equation for sodium sulfide. If a compound has a polyatomic ion, they stay together. Remember, polyatomic ions are covalently bound, just carrying a charge. When I see this formula, Na2SO4, say the name, sodium sulfate. This is a polyatomic ion called sulfate. The reason I stress that is when I say the name, I can hear the ions that come out. Sodium, 2 units of a +1, and sulfate, 1 unit of a -2. The dissociation of a polyatomic ion, 1 unit of a sulfate for every 2 units of a sodium. And I represent those as charged ions in the dissociated form. When strong acids dissociate, remember sulfuric made our list of 7 strong, so I'm recognizing that it is a strong electrolyte pointing to the right. 2 units of hydrogen for every 1 unit of sulfate. The polyatomic ions stay together when I write the dissociated form. Take a practice. Here's calcium chloride, nitric acid, and ammonium carbonate. You write that. Pause the video and write the dissociation equation and turn the video back on to check yours. Calcium chloride dissociates to give a calcium with a +2 and 2 chlorides with a -1. Nitric acid, indeed one of the 7 strong, so no equilibrium arrow, 100% dissociates into a hydrogen ion and the nitrate polyatomic ion. Ammonium carbonate. Say the name and you hear the ions that it comes out from. Ammonium is the positive polyatomic ion. 2 ammoniums, and carbonate carries a -2 charge. You have, I believe you do, a polyatomic ion chart that helps you find the names and the charges for these dissociated forms of salts. These are all strong electrolytes. Some ionic compounds, sodium chloride is one of those, dissolve very well at room temperatures. Some, as in silver chloride, don't dissolve hardly at all. We call those soluble or insoluble. In last class I gave you a solubility table. We just simply looked up positive and negative ions to determine if it was soluble. Your solubility table looked a lot like this one here. If you happen to have that, that's what it's referring to, with the positive ions coming across and the negative ions coming back. We actually worked some precipitation reactions hooking together to find if something was soluble or not. Notice that NaCl is soluble, Na hooked to Cl, but silver hooked to chloride is not. It is said to be insoluble. So this slide is reminding us about solubility. Soluble compounds are strong electrolytes. Insoluble compounds are not. Insoluble precipitates do not break apart. They do not dissociate. This might be a tool page that you might want out as we proceed. So predicting whether a compound will dissolve is not easy, but there are some charts that will help us out. The best way to do this is to test it, and that's what they call the empirical method. When in doubt, go and test in the lab. However, there are things called solubility rules, and this is the one from our textbook, or perhaps you'd like to use the one I gave you last quarter. Some general rules say these positive ions, lithium, sodium, potassium, those are called alkali metals, are always soluble. Nitrates and acetates, chloride, bromide, iodide, and sulfates, they're just giving us some general rules of what is soluble in water. And there are several slides in a row that go through and describe for us solubility tables. So what I would recommend, let's find this as we start deciding. I think that's a tad bit easier, but keep in mind also that your textbook and now this PowerPoint also has ways of predicting if something is soluble. Let me stop here and get ready for the next lesson